We repeat this analysis with symbols this time. The cross-sectional area, instead of 8 square centimeters, will be A. The distance here, the height of this little segment will be delta y, not 0.5 meters, and the height will be h, not 90 centimeters. So we're going from this state where the height of the column is h to this state where the height of the column is h minus delta y. And the water up here is now gone. Actually, it's still there. It's still pretty much at the top, but it's been replaced by water coming out of here at velocity v with some kinetic energy. The potential energy loss between this state and this state will be equal to the kinetic energy gain here, at least in this model. In the real world, things don't work out quite that smoothly, as you'll see when you do the experiment. Okay, what's the velocity, v? Density, as we've said, is rho equals 1,000 kilograms per cubic meter. We follow the same sequence of calculations as before. The volume is A delta y, the cross-sectional area, times the thickness of that small segment. The mass is rho v, which is going to be rho times the volume, rho A delta y. We're just building up the quantities in the same order we did before. Potential energy will then be weight times h. The weight is m times g, the mass times gravity. So we have this. So ultimately we have rho A delta y g h. Remembering that the A delta y is the volume, the rho is the density, so this is mass times g times h. The change in potential energy is therefore negative rho A delta y g h. And we've repeated that here. The change of kinetic energy is the negative of the change of potential energy, again assuming that there's no dissipation of energy in the ideal case. And that's going to be equal to this expression. I won't read it to you. Right there it is. If V naught is 0, which it isn't really, but it's close, then the change in kinetic energy will be the 1/2 mv squared. Again, neglecting the small kinetic energy that mass had as it was descending. Since kinetic energy goes as the square of velocity, and the exit velocity is much greater than the velocity of the falling water, we're not making much of an error by neglecting that. Although, if you have a small tube in a large hole, then that does become significant, as we'll see. Okay, so the mass then, being rho v, tells us that our change in kinetic energy is 1/2 times your rho A delta y v squared. Rho A delta y being the rho v, volume being A delta y, as we saw earlier. So setting these expressions equal, we solve for velocity, and we get the square root of 2gh, which is, coincidentally, the speed that the object would have falling under at the acceleration of gravity from rest for distance h. And that, of course, can also be modeled by conservation of energy. Now, when we did the experiment in class, at least, well, when we do the experiment and we let the water exit the hole, the analysis of the experiment, the water's at depth h, the hole is distance y above some level surface. We let the water flow out as a projectile. From y we can find how long it takes to fall. From the range then we can find the velocity. The velocity of the exiting water will be delta x over delta t. And we're going to test whether this hypothesis is true. Delta ke plus delta p equals 0, of course, implies the velocity square root of 2gh. We're going to measure the velocity by measuring the range and the height, and then we're going to compare that with the ideal square root of 2gh. Now, what we got in class when we did this, we observed that the velocity was less than square root of 2gh. Question, why? Okay, and we'll note that the velocity was close to the square root of 2gh for the height of the water column that was actually measured by the people that measured it. The difference was, I think, about we got 1.7 when we were supposed to get 1.85 or something like that, 1.7 meters per second when we should have gotten 1.85. Okay, why should that be? Well, one explanation, some of the energy is dissipated. This assumption that change of kinetic plus change of potential is zero wasn't quite correct. Remember, conservation of energy also takes into account dissipated energy. So if there's dissipated energy, the change of kinetic energy will be less than the change of potential, as we'll see. What's the explanation for that? Well, as the water comes out of the side of the cylinder, this represents the side of the cylinder and the hole in the water stream here. Actually, the water near the edges doesn't go nearly as fast as the water in the center. So you have this core that's moving faster than the water in a layer right next to it, in a layer surrounding it. You can think of this inner core, and then the water between the inner core and a larger radius, and then that between that radius and a larger one. The water in the middle is sliding through the middle of this ring, if you wish, which is sliding through the middle of this ring, and the water is sliding against itself. Layers of water are sliding over layers of water. And there's some frictional force there. And that frictional force is what we call the viscous force. And it's that viscous force that's probably responsible for most of the difference that we observe between the velocity of the exiting water and the ideal velocity, where we assume there's no dissipation of energy and the potential energy change is just equal to the kinetic energy change, the negative of the kinetic energy change.